In this section, we will discuss about types of functions. And in the previous section, we have learned about functions, and the functions are divided into some categories. And first thing, it is one function. Its definition is a function f from x to y is called one, or injective. And another name is injective if and only if different elements of x have different images in y. Otherwise we can say if x1 is not equal to x2, x1 and x2 are elements of the set capital X. If x1 is not equal to x2, that implies f of x1 is not equal to f of x2. That means if elements are different, then we will get different images. Otherwise we can say if elements are not different, sorry, here it is given like this: if elements are different, x1 is not equal to x2, then f of x1, that is their corresponding images, also different. Otherwise we can say if x1 x2 belongs to x, equally we can say f of x1 is equal to f of x2, that implies x1 is equal to x2. That is, if images are same, then we can say that their corresponding elements are also same. We can explain this also by using an example. Suppose there are two sets A and B, and function is defined like this. This is function, and here 1 2 3, and here 4 5 6. Here 1 is related to 4, 2 is related to 5, and 3 is related to 6. Here one element in the first set is related to different elements in the second set. That means if you can see here 1 and 2 are different, and their images are also different, and that is 1 1. One element of A have one image in B. That is different images we can see. And if you are considering another example, here it is A and B, this function 1 2 3, and here 4 5 6. Suppose here the images of 2 and 3, that is same, that is 5. That is, two elements have same image in B. So here we cannot consider this function as a 1 function. This is not 1 function. Next one, many one function. A function f from x to y is called many one if and only if two or more elements of capital X have same image in y. In another words, a function f is from x to y is called many one if and only if it is not 1. So second example we can consider here. Here 2 and 3 have same image in y. That is, many elements have one image in B. So many have one image. So here we can consider this as an example of many one function. And next one, onto function. A function f from x to y is called onto or surjective if and only if each element of y is the image of at least one element of capital X. That is, if and only if codomain of f is equal to range of f. If and only if, otherwise we can say if and only if y is equal to f of x. So onto function is defined on the basis of second set. That is, when we consider the first example here, it is based on the second set. Here second set 4 5 6 are there. So all the elements in the second set must have a pre-image in the first set, then only we can say it as onto. So here 4 has one pre-image, 5 also has, and 6 also has one pre-image. So we can consider this as onto function. But what about here? Here second set the same elements are there, 4 5 6, but here 6 doesn't of any pre-image, so we cannot consider this as an onto function. Next thing, it is into function. Its definition is a function if from x to y is called into if and only if there exists at least one element in y which is not the image of any element of x. We can use the same example that is also defined on the basis of second element. There should be at least one element in the second set and which does not have any pre-image. So here, when we consider here second example, here we can see the second set has three elements 4, 5, 6, and here we can see this 6 has no pre-images. That means here at least one element is there which has no pre-image. So we can say this set as this function as an into function. And what about here all the elements of set B have pre-images in A, so we cannot consider this function as into function. Next thing, it is one correspondence, otherwise bijective. One correspondence, its definition is a function f from x to y is called one correspondence or bijective if and only if it is one and onto. That is, if a function is one and onto, then we can say it is bijective. Suppose if you are considering the same example, if you are considering the first example, what we can say about this function, it is one because all the elements of A have different images in B. And what about onto? This is also onto because all the elements in the second set, that is B, have pre-images in A. So it satisfies, this function satisfy both conditions, that is one and onto. So we can consider this as bijective. Then what about this one? This is not one also, this is not onto, so this is not bijective. And how to prove this one correspondence? Two methods are there. Either you can prove it by to prove that f is 1 we must show that either f of x1 is equal to f of x2 implies x1 is equal to x2 for all x1 x2 belongs to x. That means if you are taking two images in the second set, if they are equal, then you have to prove that their corresponding elements x1 and x2 are also equal. Otherwise we can prove this one if x1 is not equal to x2, that is if two elements are different, then you have to prove their corresponding images are different. So like that we can prove one correspondence. Another method is to prove that f is onto. We must show that either for every y belongs to y there exists at least one element x belongs to x such that y is equal to f of x or f of x is equal to y. It simply means we have to prove codomain is equal to range. Suppose when we what is the difference of codomain and range? Codomain is the collection of all elements in the second set, and what is range? Range is the collection of all images. Then if it is 1 and onto, then what we can say? If it is 1 means all the elements of first set have unique otherwise different images in y, and onto means all the elements of second set must have a pre-image in the first set. So if it is 1 and onto, suppose you just consider this example, it is 1 and onto. We have already proved this as bijective. What is the condition here? Here codomain is set of all 4, 5, 6 and its range is also 4, 5, 6. That is, if codomain and range are same, then also we can prove that it is bijective. Next, another few more types of functions are there. On first one, that is identity function. What is its definition? Let A be in a non-empty set, then the function f is from A to A defined by f of x is equal to x for all x belongs to A is called the identity function on A. What is the meaning of that? Suppose if you input some element into the function, then the same element if you are getting as its output, then we can consider this as identity function. Suppose if you are inputting 1, its output is also 1, then we can say that as identity function. Suppose if you are inputting 2, then output also 2. If input is 3, then output also 3. That means if you are inputting x, its output is also x. Next thing, it is constant function. Its definition is let a comma b to non-empty sets, then the function f is from a to b defined by f of a is equal to b for all a belongs to capital A. That means for different elements of the first set must have a unique image in the second set. Suppose if you are considering one example, set A elements are 1, 2, 3 and set B elements are 2, 3, 4, then here the image of 1 is 2 and 2 is also 2 and 3 is also 2. That is, all the elements of the first set have a constant element, otherwise a constant image in B. So here we can consider this function as a constant function. And next one, equal functions. What is the meaning of equal functions? Its definition is two functions f and g are called equal, or written as f is equal to g if and only if domain of f is equal to domain of g, and second one, f of x is equal to g of x for all x in domain of f or g. That is, suppose two functions are known as equal, then when we consider the domain of f and g, then both should be equal, and when we consider its range, then also we can see their the images are same. Otherwise we can say the functions are called unequal. We can write it as f is not equal to g. Suppose here one example is given there, we can go through that. Let a is equal to 0 to 1, b is equal to 1, 2, 3, 4, 5. Function is defined from a to b, given by f of x is equal to 2x plus 1, and g of x defined as x square plus 1. So when we consider f of x, then here if you input 0 into that function, then what we are getting as output, that is 2 into 0 plus 1, that is 1 we are getting. And suppose if you are inputting 2, then it should be 2 into 2 plus 1, that is 5. That is, here we are getting first element as 1, first image as 1 and second image as 5. And if you are inputting these two elements in the second function, then if you input 0 here, that is 0 square plus 1, that is 1 again we are getting, and if you are inputting 2, that is 2 square plus 1, that is 5 we are getting. So here we are inputting 0 and 2, that means domain, both the cases domain is same. And what about the collection of f of x and g of x? F of x we are getting as 1 and 5, here 1 and here 5, and g of x we are getting also as 1 and 5. So we can write f of 2 is equal to g of 2. That means both the functions are equal. And next one is zero function. By name itself we can say the condition for any element in the first set, if you are getting its image as 0, then we can consider it as a 0 function. That means if you are inputting 1, then its output should be 0. If you are inputting 2, then output should be 0. In general, we can say if you input any x, then its output should be 0.